any bounded input, we would have a bounded output. This system, it's called stable according to Bible stability. If you have any input, any bounded input, if there is at least, so this, for this system, this is stable. If you have at least one bounded input that can give you unbounded output, then this is unstable. It's not stable according to Bible stability. So let's say, like, okay, we have a system that for a unit, let's say for like a sine of t, it would give us a stable output, but like for sine of 2t or sine of 200t, it would give us an unstable output. This is still an unstable system. If for all the bounded inputs we have bounded output, our system is stable, otherwise it is unstable. Okay, so how can we find out if a system is Bible stable or Bible unstable? Again, this relates to the position of poles. If all the poles are in left hand plane, then it is Bible stable. If you have at least one pole in right hand plane, it's not stable. Okay, so if you have any pole here, if all the poles are on the left hand side, this is Bible stable. Shouldn't be like this. If you have at least one pole on the right hand plane, that's not stable. What if you have poles on the imaginary plane? On poles on imaginary axis, this basically tells us that we can find an input, a bounded input that makes the system unstable. So it means that the system itself, it's not going to be Bible stable. So you might have some inputs that give you stable response, but you can definitely find an input that would give you unstable response. So the system itself, it's not going to be Bible stable. So this is also not Bible. Okay. So that's another definition for stability, Bible stability. Let's look at examples for that. So g of s is equal to 2s divided by s2 plus 1. Okay. So usually, like, we show the poles. So like what are the zeros of the system? S equal to 0. What are the poles? S equal to plus minus j or plus minus I. So we have two poles here. Usually we show poles using cross, and zeros here. Okay. So this is what we have. This is our transfer function. Now let's look at u of t is equal to sine of t. Is this bounded or not bounded? It is bounded, right? It's between plus and minus 1, right? If I take the Laplace transform of this one, it's going to be 1 over s2 plus 1. Okay, for sine of alpha t, Laplace transform is alpha divided by s2 plus alpha 2. I think it's alpha 2. No, sorry, alpha, sorry. I might be wrong, so like you can look at your table. Anyways, this is our input in the frequency domain, right? And this is the excuse me, this is our transfer function. So y of s, it's gonna be u of s times g of s. It's gonna be equal to 2s divided by s2 plus 1 squared. Okay, and I don't expect you to be able to do this kind of inverse Laplace transform. It's not that difficult, but I'm just going to give you the answer. If you find the inverse Laplace transform of this one, y of t, it's going to be equal to t times sine of t. Okay. Now, is this bounded or not bounded? It's actually not bounded. In this case, if I draw y of t, it's gonna actually look something like this. It goes to infinity as t goes to infinity, right? So you see that like if you have poles on the imaginary axis, you can find an input that makes your output unstable or unbounded. You can find a bounded input that makes your output unbounded. If you have all your poles on the left hand side, your output for any bounded input, it's going to be bounded. If you have poles on the right hand side, your output is always going to be unbounded for any bounded input. If you have poles on the imaginary axis, your output might be bounded for some bounded inputs, but might be unbounded for certain bounded inputs. Okay, so that's the definition of bibostability. In the closed loop systems, we look at the bibostability. So let's just move on to another concept. So this is like about poles and zeros, the effect of poles and zeros on the stability status of our system and our output. So you just like by locating where the poles of the transfer function are, you can just make a decision about the stability of your response and the stability